When my task, what would happen if I put two wires next to each other, two current carrying wires next to each other? This is not the case in this picture, but kind of I'm using it for illustration. Let's take the first wire. Notice the current is going up, so the direction due to the magnetic, the direction of the magnetic field due to that current is as designated by these arrows here, these arrows and the circles. Now, let's put another wire, this one here. In this case, we have a current going in the downward direction. Of course, that wire is going to result in a magnetic field as shown. But let's not focus on that in this instant. Let's focus on the magnetic field due to this wire. If I keep on extending the circles, okay, let me try to use the same color, the blue color, to represent the magnetic field lines. So the magnetic field line is going to be like this. And so I'm going to make a large loop. And it's going to be like this. So the second wire here is going to feel a magnetic field, or is going to experience a magnetic field in this direction that is due to the first wire. Now, the magnetic field due to the first wire is given by mu0 I over 2 pi r. Let's call it I1. So it's mu0 I1 over 2 pi, and let's call it R1, R1 being the distance away from wire 1. Okay, now, what do we have here? We have a current, a magnetic field. So this wire, the second wire, should experience a force. We can use the right-hand rule for that force. Our thumb is going to point down, our fingers are going to point into the screen, so the force is going to point towards the right of the screen. It's going to point in this direction. And that force, we have learned to express it before. It's going to be I, B, L, sine theta, but they are perpendicular. The magnetic field is perpendicular to I in this case. So it's IBL. Now, of course, I is the current in wire 2, so let's call it I2. B is the magnetic field due to wire 1, so let's change the labeling and let's call it B1. L is going to be the length of wire 2, so it is L2. Now, if I combine these equations, the force experienced by wire 2 is going to be I2 times mu0 I1 over 2 pi R1 times L2. Okay. Now, similarly, I can do the same analysis to describe the force experienced by wire 1 due to the current in wire 2. Okay. The result is we come up with this equation. That's called the Biot-Savart law. It is mu0 I1 I2 L over 2 pi d, where d is the separation of the wires, I1 the current in wire 1, I2 the current in wire 2, L is the length of wire, so if we are calculating the force on wire 2, it's going to be L in wire 2. If we are calculating the force on wire 1, it's going to be L on wire 1. Usually, we are going to worry about the force per unit length. As you notice in this one here, we had currents in opposite directions, and as a result, the force was pointing in this direction. Essentially, we are seeing that wire 1 is repelling wire 2. So actually, we can do the analysis, but when the currents are in the opposite direction, the forces are going to be attractive. The force on wire 2 is going to be towards wire 1. The force on wire 1 is going to be towards wire 2. But then when the currents are in opposite directions, it's going to be a repulsive force. Okay, let's look at a simulation of this. Okay, now in this particular case, what we have is, let's set up currents in the same direction. So both of these ends are connected to the positive lead, so they are going to carry current in the same direction. So when we run it, when we shut off the switch, look what's going to happen to the wires, and they attract. Okay, now we can pause it. Why do they attract? Again, using the right-hand rule, if I have my thumb going in this direction, and then I wrap my hand around that wire, the wire on the right. So that shows me the magnetic field due to that wire in the location of the second wire is pointing up. Now I'm going to focus on the second wire. Fingers are pointing up. That's the direction of the magnetic field due to the wire on the right. Thumb is again in this direction, moving towards the screen. So the force is going to be in this direction towards the wire on the right, and we have attraction. Now, if we make the opposite connection, where the current on this one is going to go in this direction, and the current on this one is going to go in the opposite direction, okay, this way and this way. Now here, this wire here, we have the current in the same direction as we discussed a moment ago. So the magnetic field on that wire is still upwards, but then the current in that wire is away from the screen or towards us. So we have to flip our thumb should be towards us, and you'll notice that the force should be in the opposite direction, or repulsive force.